I welcome back all to the course on Control System Engineering. In this video, we are going to learn the signal flow graph representation of a given control system, and using this signal flow graph method, we are going to learn how to derive the transfer function of a system using Mason's gain formula. Let me explain first of all what is meant by signal flow graph. Signal flow graph is nothing but it's a alternate representation of the block diagram to show the relationship between different variables in a system. So it's a diagrammatic representation which shows the relationships between different variables of the system. And this method was developed by S.J. Mason. This method does not require any reduction technique like block diagram reduction to calculate the transfer function or overall gain. That is the advantage of signal flow graph method. That's why the using Mason's gain formula, we can easily calculate the overall gain or the transfer function of a system without using the reduction technique like block diagram reduction. And the signal flow graph in general consists of nodes, branches. Each branch is like a line connected in between two nodes. All we'll also see how to convert the given block diagram into the signal flow graph in the next coming slides. In addition to nodes and branches, there are arrows which shows the flow of the signal from one node to another node. Of course, this signal direction is also there in the block diagram representation. This is similar to that. The difference is there we are having everything in a block. Every system gain is represented in a block way, block diagram, rectangular box. Here, everything is like a branch. We'll see that how to represent a system in a signal flow graph representation. See, this is a simple representation of a signal. Here the signal gain is G of S, and this signal is represented like a single line with arrow mark that represents the flow of the signal, the direction of the signal flow. And the signal flow graph is also consists the nodes. Wherever the variable is there, wherever the takeoff point, wherever the summing point is present in the diagram, there we can represent with a small circle or called node. These two are very important, are the major components in signal flow graph representation. We'll see the simple comparison or basic comparison of block diagram and signal flow graph methods representations. In block diagram representation, you can see a simple block. Here the rectangular box, inside we have the gain term G of S and input signal R of S, output signal C of S. This is a simple representation of a system, simple open loop system in a block diagram way. In signal flow graph representation, same thing you can represent like this. In RHS side C, this input R of S is a variable represented by a small single node, and this signal gain term, a box or block, is represented by a line or branch. You can call it as branch. Branch is nothing but a straight line or a line, a corridor line with an arrow, and this signal gain is G of S mentioned just above or below the arrow mark or line branch, and the output variable C of S. So here we have two nodes. Since we have two variables here, and in between these two nodes are connected by a gain called G of S here. Just this is the signal flow graph representation of this block diagram. Now we'll see how to convert a given block diagram into signal flow graph. The first rule, suppose in the block diagram, if you have any variable or a summing point or a takeoff point, everything we have to represent like a single node. Single node. Any variable. For variable, we have to represent a node. For summing point, we have to represent a node. And also for takeoff point, we can represent a node. And second point is wherever we can see a summing point followed by a takeoff point, these two can be represented by a single node. No two nodes required here. Separately for summing point, separately for takeoff point, no need of taking two nodes. We can combine these two and make it a single node. Because of the signal flow, these two are, after this it is coming to the takeoff point, so we can represent a single node. And but if we have a summing point after the takeoff point, we have to represent by two nodes, not by a single node. Maybe this after the summation it may go to some other blocks and all, and after that if it comes to the takeoff point, the direction may be in some other way. So if there are any connections like this, first takeoff point and then summing point, we have to consider like two nodes. These are the basic rules we have to know for converting a block diagram into signal flow graph representation. We'll see a simple example. This is the given block diagram. Now how to convert into signal flow graph. See here we have input here, reference input here. So place a single node here like this. Then for output, okay, this is the output. Here you can place an output node here over. Then for summing point, put a summing point here. See, from the first node to the second node, there is no gain here. Gain is not there means one you can keep. Okay, if nothing there, no gain means it's a unity gain, one. Simple straight line indicates unity gain. After this summing point, I think better to give the numbering, then you can clearly understand. This is the first node, this is the first node, okay, and this is the second node. So this is the second node. In between we have a straight line, no gain, I mean straight line means unity gain. And this is next summing point considered as a third node. In between third node we have a block. Say this whatever a number or a function, will simply denote it as g1 for our simplicity, for better understanding. So mention it as g1 and see the flow, the direction from second node to third node, the direction is in this direction. So in the same direction we have kept an arrow mark. Then fourth node is again a summing point. This is the summing point. From 3 to 4 node in between we have G2 of S. So G2 of S in this arrow mark direction. Next, at this fourth node we have another input. Okay, this is another input direction shown, but since that input is not mentioned, we have not also shown clearly, but indication is mentioned here. And next, fifth, see here we have two takeoff points, adjacent node, adjacent takeoff points. So we can consider it as a single takeoff point like this. So this is fifth node. Of course, last is the output node, that is also nothing but this node only. So this is again you can say a output node. Otherwise you can put one more straight line here and you can mention that is a sixth node with a gain 1. Everything is both are same only. Here 4 to 5 we have a gain term G3. So G3 is in this direction. And fifth to, see here, third we have a feedback. Fifth to third we have a feedback like this. Of course here it is mentioned down, it is mentioned up, anyways, okay, no problem. And the gain of the feedback is 0.1 mentioned here, but it is a negative feedback. So here negative 0.1. Here minus mentioned here itself, because here there is no summing point indication. Summing point and takeoff point both are like similar. So we can't differentiate these two in signal flow graph representation. Therefore, and at the time of gain only, we have to show this sign, negative or positive. From fifth to second node, again we have a feedback, that is unity feedback, but here see it is negative feedback, so -1 is indicated here. This is the way of converting a block diagram into signal flow graph. You'll see some other next example, one more example. Here this is the block diagram given, and how to convert this. Similar way, this is okay. I'll mention again 1 2 3, then you can clearly understand. See here, this is the first node 1, that is a reference input R is given here, and this is second node summing point. Here again summing point is taken as a node here. In between 1 and 2 we have no, straight line is there, that means unity gain. And the next summing point is considered as third node here. At this 2 to 3, what is the signal? Nothing is there, simple, it is a straight line, so gain is 1. Next here it is fourth node, summing point taken as the fourth node. So between 3 and 4 we have G1, so G1 is mentioned here, is a branch. And next it's a takeoff point. I told you already, if summing point followed by a takeoff point, both can be considered as a single node. So a single node, fourth node only, this is not taken as a fifth node again. Next, here this takeoff point is a fifth node. Now from fourth to fifth we have G2, fourth to fifth, this is a 5. Fourth to 5 we have G2, and take this is summing point as a sixth node, this is sixth node, and this last Y output you can take it as seventh. Okay, this is for output Y. Now in between 5 and 6 we have G3, 5 and 6 we have G3, 6 and 7 we have nothing, that means straight line, unity gain. Now let us take this 6 and 4, what is there here? Just 4th to 6th, not from 6th to 4th. See the direction of the arrow mark, 4th to 6th the signal is. So 4th to 6th, what we have? A G4 gain mentioned. Next, from 7th to 4, 7th to 4, what we have? Negative feedback. So 7th to 4, either 7th to 4 you can mention, otherwise this summing and takeoff point is considered as a single node. From 6th also you can mention, both are correct. 6th to 4, it is negative feedback minus H2. Similar way, 6th to last second node, 6th to second node we have negative feedback with gain 1. This is the way we can convert any given block diagram, either complex or simple system, you can convert easily into signal flow graph representation. Now we'll see the terminology used in signal flow graph representation of a system. The input node is nothing but a source node which is having only the outgoing branches. In the given example in the bottom of the slide, you can see X1 is the input node or source node. Similar way, output node is nothing but which is having all incoming branches. It is also called sink node. In this example, X4 is the output node. A path is nothing but the continuous unidirectional succession of branches along which no node is repeated. No node appears more than once. So it's a continuous path in between any two nodes having in the middle any number of nodes, but no node should be repeated. That is called a path. In this example, see, this is a path. Here from x1 to x4, in the middle of this x1 and x4, we have a path. In this path, in the middle, x2, x3 also occurred, but these two nodes occurred only once. That is nothing but a path. This is also a path from x1 to x4. We have one more path, x1 to x2, then x2 to x4. So from in between x1 and x4, this path existed. In the middle, we have only one node, that is x2 node. Next, coming to forward path. What I mean, of course, one more path is existed in between x2 and x4. You can path is not compulsory that input node to output node. Between any two nodes, we may have the path. So x2 to x4 is a path. In the middle, we have x3 node. Now come to the forward path. Forward path definitely should exist in between input and output nodes. Here x1 to x4. See, this is the path. x1 to x4 is a path. There is a path. In the middle, x2, x3 node occurs. So this is a path. Of course, two or more paths also exist. Forward paths exist sometimes. So this is a path, and again we have one more path, a forward path like this. In between x1 and x4, we have this path, x1 to x2, then x2 to x4. This is also a forward path. Forward path definitely should be in between input and output nodes. Then feedback. Feedback path is nothing but if you start a path at one node, after uh, traveling to some other nodes and after crossing some nodes, it should come back to the origin node. That is called feedback path. In this example, the signal started at x2, say, and it is traveled to x3, then from x3 to again it came to x2. This is called a feedback or feedback path or feedback loop. This is a feedback loop in this example. Also, we have one more loop called self loop. Feedback loop and self loop both look similar, but there is a difference. In a feedback loop, the in the feedback loop we will have in general more than one nodes, but in self loop we'll have only one, one node and one branch. The origin node only is the end node. I mean, there is no middle nodes occur in the path, and it is having only one branch. In this example, see, this is a self loop. That means at x3 signal is started and it is a single branch and again ended at x3 node. In the middle, there is no other node and other branches, only single branch, single node. And gain. What is the gain of the branch, or it is also called transmission function of the branch or a path? Gain is nothing but what is the value mentioned on that branch, particular branch is called a gain term. That means if there is a path, I mean, so for example, if you take this self loop only, the gain of this self loop is A33. That means the gain of all the branches covering this path is called the gain of that branch. The path, if the path is having more number of branches, then path gain is a product of all the gains in the path, like this. See, this is the path. X1, X2, X3, X4 is a path. In that path we have 1, 2, 3 branches. So first branch gain is A21, second branch gain is A32, third branch gain is A43. So the product of these three gains is called path gain. Then loop gain. This is the loop gain. This is the loop. In this loop, how many branches are covered? Only two branches. The product of these two gains of the branches is called this loop gain. Next, non-touching loops. Non-touching loops means if two loops, suppose if more than one loop exists in a system, if suppose two loops are very far away and not having any common node, then the two loops are called non-touching loops. Simply isolated each other. That is called non-touching loops. We'll see one example and we'll find different what we have seen input node, this terminologies and all. We'll find from this given example. First, what is the input node? Then we'll find the output node. Then what are the forward paths exist in this example, and how many feedback paths and what are those loops, and determine the loop gains of the feedback loops. Of course, after finding what is the loop gains and path gains of the forward paths and what are the non-touching loops, all this will identify from this example. First, of course, input node and output node. Input node is this R of S and output node is C of S. Over. Then forward paths. How many forward paths are there? There are two forward paths. One is from R1 R input to output. This is the forward path. The forward path must be exist in between input and output. See, this is a straight line. If you see the straight line here from R to C of S, there is a single unidirectional path. This is a forward path. So this is a first forward path. Then we'll search for another path if another path exists or not. See, after at this node there is a diversion. One more signal is there, but it is incoming branch. So this is not come under forward path. This is forming a feedback. So this is, we can't come like this. Okay, we'll come in a single way like this, and at this point, if there will search, is there any possibility to divert the signal from this? It can't go like this, it can't go like this also, so it should move like this. So till this path is a straight line forward path, but at this point it can travel in this direction. Instead of this straight line, it can go in this direction and can reach this node and can go in this way. So this is the second path, forward path. So these are the gains of the forward paths. In this, the product of the gains in the first forward path, G1, G2, G3, G4, G5 and then G7. This is first forward path. In the second forward path, we have G1, G2, G3, G4, then G6, then G7. This is the gain of the second forward path. Now we'll see what are the loops, how many loops exist. Here, loop nothing but we just learned that loop is having the starting and ending node is same. Here at this point we have a feedback loop. So this is a feedback loop, and again here at this point we have outgoing and incoming signal. This is another loop, and also the next node at this point we have a signal like this, and it can't go like this, so it is not the feedback path. It is a feedback path coming in this direction, and till this point this is a feedback path. Okay, this is a feedback path. And also we have one more feedback, like from this point to this point you can go and come this direction and can go like this. So we have to search all the possibilities where the loops exist. So it's by the practice we can easily identify what are the loops and how many loops exist. But by the arrow mark, if you follow simply the direction of arrow mark in all possible ways, then you can easily find out whether there are path loops exist or not. If exist, what are those loops? So this is the first loop we identified. That loop gain is G2 into H1, and second loop is this one. Product is, loop gain is G4 into H2. Third loop is this one, and it is the loop gain is G4, G5 and H3, and this is the final loop. So the loop gain is G4, G6, H3. These are the four loops exist in the given example. And let us come to the non-touching loops. In this example, we have four loops. In these four loops, any two are non-touching loops or any three non-touching loops are present. Let us look at this point. See, this is the first loop. Whether this loop is non-touching to the remaining loops or not, or at least one loop it is non-touching, that we'll see one by one. So this loop, this is the loop, and second loop is this one. These two are completely isolated. You can see this is not touching this at any point. So there are no common node for these two loops. Therefore, these two are called non-touching loops. So the non-touching loops gain is equal to Z2H1, first this one, into G4H2 into G4H2. These are the two non-touching loops. And second non-touching loops. See, take this first loop and the third loop will compare. This is the third loop. So this third loop and first loop also non-touching. So again non-touching loops gain is same thing, first loop and second loop gain product. Then we'll compare first loop and fourth loop. First loop and fourth loop is this one. Fourth loop is this one. This is again non-touching with the first loop. So again these two are non-touching loops. So the non-touching loop gain is first loop gain into the second fourth loop gain. So we have three non-touching loops, and also we'll verify the second loop and third loop. This is the second loop, and the third loop is this one. If you see the second loop and third loop, this node is common and this node is common, right? Therefore these two are not non-touching loops. Similar way we'll verify second loop and third loop, second loop and fourth loop. This is the second loop and fourth loop is this one. Again these two nodes are common to the two loops. Therefore these two are not the non-touching loops. Then we'll see third loop and fourth loop. All possible loops will compare. This is the third loop and this is the fourth loop. All nodes are touching. Three nodes are common to the two loops. Therefore these two are not non-touching loops. So we have finally concluded that only three non-touching loops exist. Now this is another example. You please identify the input node, output node, forward paths, feedback paths and self loops, and also determine the loop gains and forward path gains. This is for your practice. This is a small, you just practice it. I'll go through quickly through the slides. Forward paths, then loops, self loop also a loop. Then this is again a loop. This is again a loop. This generally we can't identify, but if you see carefully observe this, you can find it's these critical loops. This is again a more critical loop. You can see this is a big loop. It is traveling from this point, from this point it's going this way, and it is going this way and coming here and coming here and reaching the same node. So this is a loop. This is a big and critical loop we generally can see in the complex problems. All possible loops we have to identify. This is again one more loop. So from this node it came to this node and this node, and they reach the same node. This is the self loop. These are the loop gains, and this, of course, all these are the loop gains. Now we'll see the Merson's gain formula. So what is the purpose of using the signal flow graph representation? The signal flow graph representation reduces the burden of block diagram reduction technique. That means in the block diagram reduction technique, to find the transfer function, we have to use many reduction techniques and we have to follow some steps. In every step we have to slowly reduce the number of blocks, and finally you should get a single block. That is the block diagram reduction technique. But that is very complex. Every time to draw the block diagram, and every time how to know or to reduce using different reduction formulas, it's very difficult. So to reduce this burden, the Emerson's formed a gain formula to simply write the gain formula, gain or transfer function formula from the given signal flow graph representation of a system. That is the advantage of Merson's gain formula. This is the gain formula given by the Merson. In this, the transfer function is given by C of s by R of s is equal to summation of pi into delta I divided by delta, where n is the number of forward paths. Of course, we'll find the forward paths from the signal flow graph, so number of paths, and p is the path gain. Pi is the ith path gain. We'll have number of forward paths. So first forward path, second forward path, the gain of these forward paths given by pi. Then delta indicates, of course, I explain what is meant by delta and delta I. Both are mentioned the determinants of the system and forward paths. Let me explain what is meant by this. Delta is nothing but it's calculated by 1 minus the sum of individual loop gains plus sum of the product of individual loop gains, two non-touching loops gains. There are two non-touching loops, those products, and summation. Then minus sum of three non-touching loop gains plus and so on. So this is the way we'll calculate delta value. And delta I is a similar way we will calculate, but it's a value we have to calculate only for which does not touch the forward path I. Since we are calculating delta I, the non-touching loops what we have used in the delta formula should not touch the first ith forward path. That is the condition. Remaining delta formula is same only. This is the Mason's gain formula. Now we'll apply on a problem. So before that, let us know the procedure how to proceed it. First, we have to calculate, identify what are the forward paths in the given signal flow diagram, and what are those forward path gains, PIs, P1, P2, and so on. We have to calculate. Then we have to identify the loops and we have to calculate the loop gains. Then third point, non-touching loops we have to identify. 2 non-touching loops, then 3 non-touching loops, and so on. We have to find it and keep that aside by calculating the non-touching loop gains. Then in the sixth point, we have to calculate the delta value as per the formula. Then seventh step is we have to calculate the delta value for each path, delta 1, delta 2, and so on. As many number of forward paths are there, we will have that many number of delta values. Now we'll see a simple example here. This is the given signal flow graph. Now we have to calculate the transfer function of this diagram. First we'll identify how many forward paths. Forward paths, we have 2 forward paths from first node to forward path is nothing but a path from input node to output node. See what are the forward paths here? It will travel from this place to this place. It can't go this side and this side, so it should move to this side only. From here it will go like this or like this. So we may have two loops, two forward paths, remember, but for the first time we'll go straight and like this, like this. So this is the first forward path. So the gain of this first forward path is 1 into G1 G4 into G2 into 1 into 1. So totally G1 G2 G4 only. The second forward path, it is coming like this, and it is moving like this, G3, and it is going to C. So the loop forward path gain is, second forward path gain is G1 Z4 G3. So G1 G3 G4 is the second forward path gain. So 2 forward paths found, no other forward path identified in this diagram. Now we'll come to the loops. Of course, from this you can simplify the formula like this. No need to put the summation I is equal to 1 to 2 like that. We can write simply P1, we have 2 forward paths, so P1 delta 1 plus P2 delta 2 divided by delta. We have to find delta 1, delta 2, and delta now. So to find the delta, we need the loops and loop gains and then non-touching loops. So we'll first identify the loops. What are the loops here? See, from this you can identify one loop, first loop, and at this point, of course, these two are in parallel only, not the feedback. So but here we have one more feedback coming back. So it is starting at this node, going this way and coming like this way. So this is one loop, and also we have one more like this path. So from this path to G3 and going this way and coming this forward feedback and coming this. So one more loop. So totally we have 3 loops, L1 simple, G1 G4 and H1. Second is G1 G4 G2 and then minus H2. So minus G1 G2 G4 and H2. Third loop is G1 G4 G3 and then going to minus H2 coming back. So G1 G4 G3 and minus H2. This is the third loop. Now we'll see what are the non-touching loops. Before going to the formula, let us conclude whether there are non-touching loops or not. Sometimes will not be there, sometimes it will be there. In these three loops, this is the first loop and second loop. Second loop is this one. Both are touching at this node and at this node. So these two are not non-touching. And identify first loop and third loop. This also both are having common nodes, so no non-touching. Then second loop and third loop. Again non-touch, both are touching, so there is no non-touching loop in this example. So simply the formula is simplified like delta is equal to 1 minus of sum of the individual loops. If there are non-touching loops, what should we do? We should keep plus of the sum of non-touching loop gains. That we should write. But here no non-touching loop, so third term is not there. Simply delta is equal to 1 minus of sum of individual loops. This is the one. Sum of the loops L1, L2, L3. Therefore, delta is equal to, after substituting L1, L2, L3, we will get like this. So you can simplify this also. Similarly, we have to find delta 1. Delta 1 is nothing but same formula, but here this non-touching loops should not, this individual loops or non-touching loops, any loops should not touch the first forward path. That's what. Simply eliminate the first forward path. If you eliminate the first forward path, any loops exist? No loops exist. See, because the first forward path is R1 to C, R to C. This is a straight line. If we remove the straight line, where are the loops? No loops exist. Therefore, no loops here if we remove first forward path. So we have only 1 minus 0. Simply it is 1. Similar way, if you remove the second forward path is this one. If we remove the second forward path, again there are no loops. Therefore again it is 1 minus 0. So delta 2 is also equal to 1. Therefore if you substitute now in this formula, we will get like this. Simplify and we will get finally the transfer function R by C by R is equal to G1 G4 into G2 plus G3 whole divided by 1 minus G1 G4 H1 plus G1 G2 G4 H2 plus G1 G3 G4 H2. In this let us before concluding this session, let me explain, let me recall what we have learned in this video. In this video, we have learned what is meant by signal flow graph and why it is used, why it is required, and we also have learned what are the different terminologies used in the signal flow graph representation, and we also learned what are the rules and how to convert the given block diagram into the signal flow graph representation. And also we learned what is the Mason's gain formula and how to get the transfer function using Mason's gain formula. In the coming video, we will learn different examples using Mason's gain formula, how to get the transfer function of the given systems. Thank you.